Hi guys, in this tutorial we're going to look at the dot product. At the end of the tutorial you should be able to work out a question like this one, which is basically just the application of dot product to work out an engineering question. Now what is a dot product? Well, this is a build up on what we have been doing so far in terms of engineering. So suppose you had a vector expressed in Cartesian vector form. So you have a vector A, and this vector A is going to have components, let's say A in X. So A in X is in the I direction, and then you have A in Y, which is in the J direction. Then you have A in Z, which is in the K direction. Then you have another vector B, and this vector B, let's say it has components B in X in the I direction, and then B in Y in the J direction, and then we have B in Z, BZ in the K direction. So the values here, that's AX, AY, AZ, these are just components, the magnitudes, they're not vectors, they're just numbers. And then to show direction, we have the unit vectors I, J, and K. And then also the same thing goes for BX, BY, and BZ. Now, suppose what we wanted, or what we found a question where they are asking us to evaluate the dot product between A and B. Well, in mathematics, a product can be, in this case, we're going to look at it in two forms. We're going to look at a dot product, which is what we're looking at in this tutorial. And the other one that we're going to see is going to be a cross product. So we're going to see a cross product in later videos. Now, what happens during a dot product? Well, in simple terms, a dot product will always give an answer such that you're literally evaluating the two vectors. Let me just write them side by side. So here you have A in Y, A in Z. Let's do the same thing for the vector B. Now, for us to get the dot product, well, you can use the same multiplication where A in X multiplies everything here. But this builds on the fact that if you have I dot I, if you have something like this, the answer that you're going to get here is going to literally just be 1. But if you have I dot J, literally a situation where you are dotting or you're getting the product of two unit vectors which are not the same. In this case, this is going to give us a 0. So if you were to expand this, if you were to expand this and then taking into account that when the unit vectors are the same, then their dot product will be 1. And when the unit vectors are different, the dot product will be 0. So even when you end up with, let's say, I dot K, this is going to also be giving you a 0. What you realize is that the expansion of this expression will reduce to only A in X, where this will be multiplying B in X. In this case, notice that we're going to have I dot I, and just as I was displaying earlier on, I dot I will give us 1. So this can just be left out. Then plus, this is B in X, then plus, again, in terms of A in Y multiplying everything the other side, we're going to see when A in Y multiplies B in X, notice that the unit vectors will be different, so this will be 0. But the only term that will survive will be when A in Y multiplies B in Y. So we're going to have A in Y multiplying B in Y. For this case, the unit vectors will be the same, J and J, so J dot J will give us a 1. And then lastly, the other term will be A in Z multiplying B in Z, and in this case again, this will be the only term that will survive from that multiplication. So this is what we're going to have. Again, K dot K will just be a 1. So this is how a dot product will simplify. Notice that it's as if we're just multiplying the corresponding components. The X component multiplies the X component, and the Y component multiplies the Y component respectively, and the Z and so on. Now, this is literally how it goes. We can even give an example where we have a vector A, and let's say this vector A has components, let's say 4i minus 3j. Then let's just leave it there. And then we have another vector, and for this vector, let's say it has components 2i minus, let's say 5j, and then let's say plus 4k. In this case, the absence of a k component implies that what we have here is actually a 0. So if we were to evaluate a dot b, in this case, we're going to end up with the I component will multiply with the I component. So that's 4 by 2, that's 8 here, plus, then we have minus 3, the j component, will multiply the other j component, which is minus 5, plus, and lastly, the k component, that's 0 by 4. So in the end, that's a dot b ends up being 8. This is going to be positive, plus 15, and this is going to be 0. So that the summation here ends up being 23. Notice one thing here. The dot product between two vectors gives an answer which is not a vector. So this is just going to be a scalar quantity. Now, how do we actually take advantage of this from an engineering point of view? Before we get there, there is one actual thing that you can that we are going to see a lot when it comes to dot product. That is the other way that actually the dot product simplifies. It can be shown that if we were to expand the dot product, this one, based on what we saw earlier on, as in the components multiplying each, the dot product of this will literally be the same as if we got the magnitude of the first vector, multiplied it with the magnitude of the second vector, now just magnitudes, and then multiply them by cos the angle between them. This can be shown. But what we need in engineering is just to know how to use this expression. So, of course, again, the dot product of A and B will be equal to the product of the magnitude of A times the magnitude of B. So these are just magnitudes, not vectors. So the magnitude of vector A times the magnitude of vector B, then multiplying cos the angle between the vector A and the vector B. So in this case, let's say you have two vectors. One vector is this, and then you have another vector, let's say something like this. So if you wanted to use this expression, of course, we're going to see an example, then you'd have to move this, move it to the tail of the other vector so that we have something like this. The angle between them gets to be this one. So the dot product of, if this is vector A and this is vector B, the angle between them is theta. So the dot product between this vector and this vector will literally be equal to the magnitude of A times the magnitude of B, then cos the angle between them. A good example that we can look at for us to understand this, let's look at this one here. Suppose we had a question like this one, where we have two ropes. One rope runs from A to B, the other rope runs from A to C, and they are tied to this this object that is at the bottom here, this pillar here. Now, of course, in this case, these ropes, of course, we expect to see we're going to have some tension there and so on. But for now, we're not really looking at the forces. Let's say our goal here was to determine the angle between the two ropes. So let's say we wanted to determine what the angle between these two ropes was. Now, how do we do that? Well, the first thing that we need is we need the two vectors. If we're going to use, of course, there are other methods we can use here. I want to point out that there are other methods we can use to determine what the angle there is. But here, let's use the dot product approach. So for the dot product to work here, we need two vectors. So let's just highlight where those two vectors are. So the first vector is going to be from A going to B, and the second vector is going to be from A going to C. So these will be our two vectors. Now, once we have our vectors, let's see how we're going to utilize these vectors. So let's say you have R that runs from A to B in this direction, and then you have the other one, R, running from A to C in that direction. So we're going to get the dot product. We're going to use the dot product of these two vectors to determine the angle between them. So let's come up with the displacement vector from A to B. So we're going to take advantage of these values which we've been given here to come up with what the displacement vectors will be. So again, this is literally just continuation on what we did last time on how to come up with the displacement vectors. But if you haven't seen that video, we can still see if we can take care of you here. Let's see how it goes. So let's start with the vector RAB. So from RAB, again, we're starting from A since we're running from A to B. So we're starting from A here. Let's demonstrate how you have to move there. So from A, notice that in the y-axis, you have to go down. So y is vertical in this case. So you have to go down. How far down? 4 meters. This 4 is shown to say that it's literally giving us the displacement downwards from A up to the origin, or let's say the bottom there, the ground. In the x-axis, I'm seeing an x here, so this is in the x-axis. So in the x-axis, you'd have to move from here coming up to this point. Notice that you have already reached B. So in other words, to move from A to B, we actually don't even get to move in the we don't get to move in the y-axis. So the x-axis, I'm seeing I'm going in the positive x, and the distance we have to cover is about 4 meters there. So for RAB, we move positive 4 in the I direction. We don't move at all in the y-axis, so that's literally just a 0, or you can leave it out. And then in the z-axis, you have to go down, so the negative, and you have to go down by 4 meters. So that is in the k direction. And if we looked at RAC, for RAC, look at what you have to do. So let's put down RAC. So for RAC, let's have it in red. So RAC, it's from A coming up to this point. So to reach that, how do you have to move? Well, the first step will have to go down. In the z-axis, you're still doing that 4 meters downwards, so it will still be negative. In the x-axis, you still have to do this 4 meters coming in this direction. So you still have to do this 4 meters. But the difference now is that you have to move in the y-axis as well. So in the y-axis, again, you're going in the positive y, and you'd have reached your point C. So this is what we're seeing here. So if we were to write that down, so we'll start with the x-axis. In the x-axis, we did this, which is positive, and it's a 4 again. So we have 4 in the I direction. Next, in the y-axis, we did the 2 meters, and it is also pointing in the positive y-axis. The first one was in the positive x-axis, the 4. The next one is in the positive y-axis, the 2. But in the z, we still did that same 4 meters, and it was downwards, so the negative. So now we have our two vectors. So how do we use, or how do we take advantage of the dot product to get the angle between our two vectors? So our two vectors, again, let's highlight them. So these are the vectors. This vector, that's RAB, and this vector, RAC. So we want the angle between them, which is this angle here. Let's label it as theta. So from the dot product, what we're seeing here is that the dot product of the vector AB and the vector RAC is equal to the magnitude of RAB times the magnitude of RAC, then cos the angle between them. So this is the one that we're going to take advantage of. So if we wanted to find the angle there, we would just have to make the angle subject. So in this case, we're going to start with cos theta being equal to RAB dot RAC divided by the product of their magnitudes. So we have RAB and then RAC. From here, of course, we see that we'll just have to get the angle. This is going to be theta will be equal to cos inverse of RAB dot RAC. Then we'll divide this by the product of their magnitude. Now, so we need two things. We need first the dot product directly, and we also need their magnitudes as well. So let's see, how do we do it? Well, let's start with their product, the dot product. So we have RAB dot RAC. So remember how it goes. Just multiply the corresponding elements or the corresponding components. The x components, in this case, we have 4 and 4. So the product there is going to be 4. So this is going to be 4 by 4. The product is not 4, of course. 4 by 4, that's 16. So you have 16 plus the next, the the j components or the y components, that's 0 times 2, that's a 0. Then we have the z components, which is negative 4 times negative 4, which is positive 16. So you have 16 here. So this ends up giving us 32. Again, notice that their dot product is just a scalar quantity. Having obtained that, the next thing that we want to get is their magnitudes. RAB, what will be the magnitude here? Well, the magnitude, just like before, it's the square root of the x component squared plus the y component squared plus the z component squared. So let's see, for RAB, the x component is 4, the y component is 0, the z component is negative 4. So for this one, we're going to have 4 squared, 0 squared, which is 0, then negative 4 squared. This is what we're going to have. In the end, this is just the square root of, this is 16 plus 16, which is 32. So the square root of 32. We do the same thing for RAC. And if we do the same, we're going to end up with the square root of, let's see, we have 16 plus 4 plus 16, 36. So we have the square root of 36 here. So in the end, we see that our theta will be equal to cos inverse of their dot product, which we saw reduced to just 32. So this reduced to just 32, then divided by the product of their magnitude. The first one, the magnitude was root 32. The second one, the magnitude was root 36. And then we simplify this. Notice that we get the angle theta just as 19.47 degrees. So this is how we get the angle between any two vectors using the dot product. Now this was probably more mathematical. Now how do we use the dot product to work out a question in engineering? Well, which takes us to the question I started by showing you in the first place. Now consider this question. In this question, they're saying that the pipe in the figure shown is subjected to the force F, which is equals to 80 newtons. And what they want us to do is to determine the angle theta between F and the pipe segment BA. So our pipe segment BA, let's see where it is. So BA is from here to here. So they want the angle between BA and the force F. So the force F is this. So the angle they want us to find is this one here, and they've labeled it as theta for us. So that's the first thing that they want us to do. And in the second part, they want us to find the projection of F along this line segment. So we'll get back to that. For now, let's find the angle between BA and the force F. So how do we do that? Well, very easy. Again, we're going to take advantage of the dot product. But to do that, what we need are two vectors. One vector has to run in the direction of the force. So we need a vector running in the direction of the force. And the other one, we need a vector running in the direction from B to A. So let's start with a vector running in the direction of the force. So how do we get that vector? Well, let's label this vector as BC. You can even just label it as an arrow pointing to C. But for now, let's just label it as arrow from B to C. So again, we have to take advantage of the little things that the diagram is showing us. And in this case, you see to say that this vector from B to C only has a few components. It doesn't have all the three components. Like for example, you see to say that perhaps the first thing that you do is to go up. You go up to this point. After reaching this point, then you go this side to reach point C. So you first move in the Z direction to go up. So you move in the Z direction to go up, meaning it's going to be a positive displacement. How far up? 1 meter, according to this one, which is to the side of the point B. And then after that, you move parallel to the y-axis to go backwards up to point C. So that is going to be a negative. You don't really get to do any movement when it comes to the x-axis. Do you now? No, you don't. So based on that, in the x-axis, you have nothing for RBC. But in the y-axis, you have to move parallel to the y-axis up to point C. And how far do you have to move? Notice that you have this one, which is from here to here. And then you have this 2, which is from here up to here, because they're telling us to say that this point is literally somewhere here, which is 3 meters altogether from the origin, if you are moving in the y-axis. So because of that, in the y, we have to do that 3 meters. So we have 3 meters, but since we're going backwards, that's minus 3. What else? In the z-axis, we had to go up, so that's a positive. So this is in the j. We had to go up, so that's positive 1 in the k direction. So if you need units, of course, you're going to do this and say that this is in meters. Then the next thing that we need is the vector running from B to A. And for this one, let's see what we have to do. So to run from B to A, what we need first, so this is literally just going up to that point, and we see that A is along the y-axis. So if we're going to do that, first we're going to go from B coming up to this vertically upwards in the z-axis, which is just 1 meter. Then we're going to move parallel to the x-axis, that x component, to reach the y-axis. Then we're going to move parallel to the y-axis, or along the y-axis. Sorry, let me take it back. Along the y-axis to reach our point A. So literally that is what we have to do. So be very mindful of how the diagram is looking and how to actually utilize the few hints they've given you. So because of that, in the x-axis, we went backwards. So that is minus 2 in the x. So that is I. And then in the y-axis, we went back again. From here, we went in that direction, which is opposite to where the y is. So because of that, that's another negative, and that was a 2 again, 2 in the j. And lastly, in the z-axis, we went up, which is literally along where the z is, towards where the z is. So that is going to be a plus 1. So this becomes a displacement vector. So this one is in the k direction for RBA. So if we need units again, this is in meters. Now, in terms of their magnitudes, we know to say the method that we're trying to take advantage requires the vectors, their magnitudes, so that we can easily get the answer. So the magnitude of RBC, so we'll just get each component squared. So the square root of minus 3 squared plus 1 squared. So this is just going to be, for this one, this is just going to be a 3. Will it? No. So for this one, we're going to have, let's do it slowly. So we're going to have 9 for the first part. This is root 9 plus this is going to be 1. So in the end, we have root 10. For the second one, the magnitude of RBA, this one now will give us a 3. So try to do it and see that you can actually get the correct answer. The units, of course, are the meters. Now that we've got the vectors and their magnitudes, again, we're going to take advantage of the expression we derived earlier. The angle between any two vectors will be equal to cos inverse of, in the numerator, we have their dot product, which is RBC dot RBA, and then divided by the product of their magnitudes. So RBC and then RBA. So we already saw this expression when we were working out the previous example, which is this expression. So based on that, we can make the substitutions. On top, we need the dot product. So the two vectors, I'll just get them as they are. So we have RBC, that's minus 3 in the j, plus 1k, and then this is dotting. Then we have minus 2i minus 2j plus 1k. Then this has to be divided by the product of their magnitudes. For the first one, the magnitude was root 10. For the second one, the magnitude is just 3. So this is the expression we're dealing with. So if you evaluate this, of course, let's start with the dot product on top. So 3j, notice that the first term doesn't have an I, so it's 0 times 2, that's a 0. Then we have negative 3 times negative 2, that's minus 6. Then we have 1 times k, that is 1. So this is plus 1, then divided by 3 root 10. So that from here, this is cos inverse of minus 5 over 3 root 10. Okay, but looking at this, I don't know if you guys were able to spot it, but notice that this is a negative term, that's minus 3, and then I multiplied it with minus 2 here. So this is a negative and a negative. So a negative and a negative, we expect a 6, yes, but we expect a positive 6. So this was expected to be a positive 6 here. So because of that, this is not going to be a 5. This is going to be a plus 7. So this is going to be a 7 here. So with that correction made, you can take the cos inverse here. And once you do that, we expect the answer to turn out to be 42.5 degrees. So this is what is going to be the angle between the two vectors, or the force and the pipe segment. Now, let's see. The second part was asking us for what? The second part was saying the projection of F along the pipe, along this segment. So they want us to find the projection of the force F along the pipe segment BA. So our force is in this direction, but they're asking us to find the projection of our force that will be acting in that direction. So it's more like we want to find a component of F that will literally be going in that direction. But how do we do that? Well, to actually work out that question, we're going to take advantage of one property of unit vector, of dot products. Well, the idea here is very simple. If you have a vector like this pointing in some direction, and then you wanted to find its, let's say, its projection or its component along some line that was heading in some direction like that. Well, to actually find the projection of this force along this line, all you need is a unit vector that points in that direction. So you need a unit vector that points in this direction. So once you get the unit vector in this direction, then the next thing that you need is you need the force itself that you're actually trying to work out. But the force has to be in Cartesian vector form, meaning you have its x component figured out, its y and z as well. So if you know these two, the force in Cartesian vector form and the unit vector pointing along the direction where you want to make the projection, then the component in that direction will just be equal to the dot product of the force itself and the unit vector pointing in that direction you want to get the projection in. This is all that you have to do. In this case, how are we going to employ it? Well, what we have is we have a force, or our pipe segment. A pipe segment is something like this. So this is where BA is. Let's say this is where BA is. And we already got what the displacement vector from B to A was. So the displacement vector from B to A in the previous calculation, we got that as minus 2 in the I, then we had minus 2 in the J, then we had plus 1 in the K direction. So this was the displacement vector in that direction. So since this is where we want the projection to be made, so we need to get a unit vector, not the displacement vector, but a unit vector pointing in this direction. So remember how we get the unit vector? The unit vector pointing along BA can be obtained by just dividing the vector RB divided by, the vector itself divided by the magnitude of the same vector. This is going to give us a unit vector running from B to A. So since we already have the original vector, we actually even have the magnitude figured out already. So this is just going to be the vector itself minus 2i minus 2j plus, I wrote kk, so this is 1k, then plus 1k. This has to be divided by the magnitude of the vector, which is a 3. So from here, the unit vector simplifies to just be minus 2 over 3 in the I, minus 2 over 3 in the j, then plus 1 over 3 in the k direction. So this is now a unit vector running from B to A. So we have figured out one part. Remember I said we need two things, a unit vector pointing along the segment where we want the projection to be made. And the second thing we need is the force itself expressed in Cartesian vector form, the original force. So where is our force? In this question, the force is here. And notice that the force is just given as a value, a magnitude. We need this in Cartesian vector form as well. So we need the original force in Cartesian vector form. But how can we actually evaluate or express this force in Cartesian vector form? Well, we already looked at questions like this. Hope you guys remember how we did that. So we already have a displacement vector pointing in the same direction as the force, that was this, and we already have its magnitude. So the magnitude of this displacement vector, we saw earlier on to say that the magnitude is just root 10. So to get the force F in Cartesian vector form, we need to multiply it by a unit vector pointing in its direction. So now just on the force is like this, a unit vector pointing in the direction of the force. Let's say a unit vector pointing from B to C. To get that, all we need is to multiply or to divide the displacement vector from B to C divided by its magnitude, R, B to C. Here first, don't confuse the two steps. Here we're just trying to express the force, that 80 Newton force in Cartesian vector form. So first we need its unit vector. So in this case, the vector itself was, that was minus 3J. Then this was plus 1K. So this will be divided by the magnitude, which we found earlier on, root 10. So the unit vector from B to C, the unit vector in the same direction as the force, will be minus 3 over root 10 in the J plus 1 over root 10 in the K direction. So now that we have the unit vector, the force F now in Cartesian vector form will be the magnitude of the force multiplying a unit vector pointing in the same direction as the force from B to C. So that's the force from B to C. So in this case, the magnitude of the force, if we go back to the question, the magnitude of the force is 80 Newton. So we have 80. So this is going to be 80 here, then multiplying our unit vector, which is minus 3 over root 10 in the I plus 1 over root 10 in the K, or this is in the J direction. So from here, we can take the 80 inside. So this becomes minus 30, not minus 30. We can take it in and divide with the root 10 as well. This is going to give us minus 75. Let's round off to 2 decimal places, 0.89. This will be in the J direction. Then this will be plus. Do the same thing for the other part. 80 will multiply this, divide by root 10 again. So give us plus 25.30 in the K direction. So now that we have the force expressed in Cartesian vector form, we can go right ahead and get the projection. So now the projection of F along the line segment BA will be equal to the dot product of the force itself, the original force, which was running from B to C, dot a unit vector that is running in that direction we want to get the projection from B to A. So our unit vector, we got it earlier on. This was, where is it again? So our unit vector BA, we got it, we had this. So this was our unit vector in the direction of in the direction where we want the projection to be made. So let's put it there. So this is the unit vector. Then we're getting its dot product with our force. And our force vector, we've just got our force vector. And that was this. So let's get this. Reduce it a bit. Okay, this is what we have. So this is the dot product we're evaluating. So again, like for like, we see I. In this case, we have I. The x component is minus 2 over 3 from the unit vector. But from the force itself, the x component is 0. So the first part is just going to be a 0. But for the second part, we have in the J direction, we have negative 75.89, multiplying in the second part from the unit vector, we have minus 2 over 3. J dot J will give us a 1, so we drop it out. Then plus, from the force, we have 25.3, and then from the unit vector, we have 1 over 3. Again, notice that the answer again, when we get the dot product, will always give us a scalar quantity. So when we simplify this, the final answer comes out. So this gives us 59.0 newtons. So this will be our approximate answer. So this is going to be the projection of F onto the line segment BA. So that will be our 59.0 newtons. Okay, so I hope you guys were able to follow through on how to work out these questions. Now try to see if you can work out this question and try to see if you can find the answer that is expected. So let me know what you find in the comment section. So of course here they're just trying to see, they're asking you to determine the angle between the y-axis. So the y-axis of course is here, and the wire segment, that's AB, and the wire AB that is here. So they want you to find this angle which is here. Try to see if you can pull it out. Let's see what you find in the comment section. All right guys, we'll see you in the next